Welcome to the practice test for Chapter 8, everyone. My students, feel encouraged to watch the video, but feel free to watch whatever part you need to. You don't have to watch the whole thing. And please try the problems on your own first as much as possible before you refer back to this video or refer to this video. But give them a shot first. I'm going to be going through every single one. I'm going to be checking my answers as I go. I am looking at these for the very first time right now, so I'm hoping I won't make mistakes, but if I do, hey, you realize, hey, I'm human too. Even as your teacher, I might make mistakes every once in a while, but I'm going to double check my work as much as possible and just make sure that I correct any mistakes that I may make. So let's see what we got here to start. So this is 1 and 2, so we're going to change 204 centiliters to deciliters. What would that look like? Over here I'm going to draw out what I think is very helpful in terms of any of these problems where we have to change units. So I'm going to use my little kangaroos, hop, ditches, but don't catch mice. So this is kilo or kilo, hecto. This is deca, which we have a little DA there. And then the B for the base, deci, centa, and milla. So this really helps it make it really easy to see how many spots I have to move the decimal place. So I need to go from centiliters to deciliters. So here's centiliters right here. I'll do this one in red, and then deciliters is right here. So that's going to be 1, 2, 3 places. I just moved the decimal place 3 places this way. A deciliter is much larger than a centiliter, and so I should imagine that my number is going to get smaller too. So that's a kind of a way to verify that that is the case. So this one I'll color code here. Usually we put the 0 before there, so I'm going to do that here too. So we have a 0 point, and then this got moved 4 places. So I'm going to write the number as it was first and show you, or 3 places, 1, 2, 3. So the decimal point's now going to get moved to there. So we have 0.204, and this would be now deciliters. So I'll just check that and we'll move on if I'm good to go. Right, so number 2, why don't I do this one? I'll do this one in green. Still going to use this over here, changing 123 kilometers to millimeters. So that's a big jump here. That's 1, 2, 3, 4, 5, 6. Going to move the decimal place 6 units. So if I start with 123, the decimal would be right here. I should add 1, 2, 3, 4, 5, 6. I'm moving the decimal place to here now. There's going to be 6 more zeros filled in here. So when I have this many places, remember if you have 5 or more digits, we want to include spaces with this. If we're going to write it like the rest of the world does it, which is what we're trying to get in the habit of here, we'd have 3 zeros, a space, 3 more zeros, a space, and then 1, 2, 3 like that. So instead of commas, using those spaces, this would be my answer. We went from kilometers to millimeters, so this would be that many millimeters, 123 million millimeters. So let's move on to number 3 now. How many times greater is a kilometer than a decameter? So I'm going to go back to this thought and rewrite that again. Kangaroos hop ditches, but don't catch mice. And this is my deca right there. So how many times greater is a kilometer than a decameter? So look at the spacing here. Looks like it is going from decameter to kilometer. You're jumping, this is times 10 for each jump. So times 10 times 100. So this is times 10. This is times 10. Together, that's times 100 right here. So how many times bigger is it for number 3? I would say this is 100 times greater. So we're good to go on that one. And now jogging. High school track is an oval that measures 400 meters around. That is very standard. That's a standard length of a track. If Dave Camp jogs around the track 6 times, how many kilometers has he gone? So those of you that are visual thinkers, this is kind of what the track would look like. Each time around, you usually have the start and finish line right about here. Then you go around once. That's going to be 400 meters for each lap. And so how many laps did he go? He's doing 6 times around, so that's going to be, we've got 6 times 400, that's 2,400 meters, but the question asks what is it in kilometers instead, so we have to change this to kilometers. Again, if you're wondering what that is, you don't remember how many spots to move the decimal. Kangaroos hop ditches, but don't catch mice. So we look at this and we notice that from meters to kilometers, that's the base unit. The base unit is meters here, so I better be moving this. Let's see, 3, 1, 2, 3 this way. So take my decimal and move it 1, 2, 3. It's going to go right there to go to kilometers. So I have 2.4 kilometers. Good job, Dave. It's a solid jog. It's a solid run right there. Moving on now, 5 through 9, choosing the best answer of these. So number 5, the length of this page. So this was your book. You're thinking of that 10 centimeters, 25 centimeters, 60 centimeters. If you recall that 1 centimeter, let's write that up here. This could be helpful, or let's actually just refer to that in one of our past lessons that we've done. So if we go back to 8.4, this table came from 8.4, our metric conversions, going from US customary to metric. 1 inch was about 2.54 centimeters. So I'm going to use that idea to help me complete this one at least. So the length of this page, 10 centimeters, if you talk about that, that's going to be 10 divided by 2.5-ish would be 4 inches. That's a little too small. So I would say it's not A. 25 centimeters, that seems to make a little more sense. 60 centimeters there's about 12 centimeters, or 12 inches, excuse me, in 30 centimeters. If you multiply 2.5 times 30, you get that. So that's a little bit too big too. So I'm going to say here, this is B, and I'll kind of show you why over here this would work using this table more. So most of the pages in books around 8.5 by 11 is kind of a normal size for paper, sometimes a little bit smaller, sometimes a little bit bigger. 8.5 by 11 inches is what I'm referring to there. So it's saying the length of this page. So if you took 25 centimeters, if we check that, 25 centimeters, and we want to change it to inches to have something that we're more used to talking about, a more customary, US customary, more customary measurement for us to think about, we would say that's 2.5 centimeters. We want to get rid of centimeters over 1 inch. I don't really feel like this work is necessary if you have a pretty solid understanding of how big a centimeter is, but it could definitely help here. So we take this and 25 divided by 2.54, take out a calculator. This is inches left on the top, centimeters canceled out, and so I would have there 25 divided by 2.54, that's going to be about 9.8, and 9.8 inches, and that seems to be pretty standard, pretty close to a normal length of the page. So I would say that 9.8, this is reasonable. Let's just call it that. Let's just say it's reasonable for the length of a page. So reasonable for the length of a page. So basically we're looking here to figure out what's most reasonable of what we have here. Number 6 then. Number 6, the surface area of the top of a kitchen table is about, is it 2 meters squared, 200 centimeters squared, or 2,000 centimeters squared? So I would say, thinking about that, let's go back to this here. We can look at this stuff and kind of figure it out from there. And we can also, I'm going to draw a picture for this. A kitchen table, I would say, generally be kind of a rectangular shape, I would guess, most of the time. So a kitchen table, they're not saying a dining table, so maybe a little smaller than that. It's not super clear how big they think a kitchen table is, but I don't think it's going to be incredibly small. I don't think it's going to be incredibly large either. So, but honestly, I think the best way to think about this one is probably process of elimination. So this 200 centimeters, you could think of that as kind of like 10 centimeters by 20 centimeters. But if you consider that to be the size of your kitchen table, are you really going to be able to eat something that's 10 centimeters by 20 centimeters? Are you going to have a table that size? No, this is way too small. This ends up being about 4 inches by 8 inches. That is much, much too small. So that would not be what we'd want. This one, you could say, what could we say there? 2,000. I think a good thing to be might be to say 100 centimeters. If you think of that, that's 1 meter. Think of a meter stick. That seems like, yeah, maybe that would be long enough to be the length of a kitchen table. But you would have to have something still pretty substantially wide. But the only way to get 2,000 from that would be to multiply it by 20. So is this a reasonable length and width for a table? I don't think so. This is the problem area. The 20 is too small. So both of these are too small. So I'm thinking this better be my answer. I'll circle that, but just kind of show a picture of how this could be a reasonable answer down here. So I would say this could be 1 meter, and this could be 2 meters. And then your area is going to be 2 by 1, which is 2 meters squared. And so 1 meter, 2 meters, that's more reasonable. That's like a little over 2 yards, so a little over 6 feet. And this way a little over 3 feet. So a 3 foot by 6 foot table, or something a little bit bigger than that, seems to be a pretty reasonable answer to me, I think. So this is just was 1 times 2 right here. This would be the 2 meters squared. So this one, I would say choice A is most reasonable. This one up here, choice B was most reasonable. Number 7, the amount of gasoline that an automobile's gas tank can hold is about, if you've ever traveled to another country or in another country, this would probably be a lot quicker of an answer for you. So I would say, like, for us in America, we'd probably say like 15 gallons maybe for a normal automobile would be about what we could hold. So I'm going to write down 15 gallons. Abbreviate that like that. I'm going to make it a fraction. I'm going to do a conversion here to see what this is in liters. So 1 gallon is about 3.8 liters is what the conversion table says. So I'm going to put gallons on the bottom. I want to get rid of gallons. I want it in terms of liters instead. So 3.8 is the liters part. That's going to go up here, 3.8. And the gallons, that was 1 gallon. So here's my unit fraction. This way I'm just changing the units. I'm not really changing the value of it. I'm just changing it so it's in a different format, different units. 15 times 3.8. Let's work that out quick. This is about 57. So 57 liters. So it kind of depends. I would say 200 liters. That's going to be way bigger than the normal automobile. And then this is a little bigger here. So smaller cars, they usually hold about 12 gallons, but some larger vehicles would hold more like 20. So if we converted 20, that would get me, what is 20 times 3.8? Just out of curiosity, 20 times 3.8 would be 76. So now we're talking more in the range. This would be closest to 75 liters. If you went and said 20 liters instead, I don't think that's a good answer, because you could take, oops, I closed my calculator. You could take 75, nope, you could take 20, there we go, 20, and if you divided it by 3.8, that would get you instead to gallons. I don't think you want to drive a car that only holds 5.26 gallons of gas. That's not going to get you very far most of the time. So this is definitely a more reasonable answer for that. Closest to 75, I would go with choice C on that one for sure. Let's start a new page here just a second. Alright, so I've copied and pasted this, and we'll do number 8 and 9 on this page. So the mass of a cellular telephone is going to be, well, I hope you can just look at choice B and say, really? 2 kilograms? 2 kilograms? I remember 1 kilogram is about 2.2 pounds. So is a phone going to weigh over 4 pounds, 4.4 pounds? It's going to weigh that much? Maybe if you're Zach from Saved by the Bell, but other than that, I don't think so. So our phones are a lot lighter than that nowadays. And then what does that mean again right there? The T stands for 1 ton, a metric ton, which is 1,000 kilograms. So 1,000 kilograms. And if you forgot that, that's coming from 8.3 right here. So we had the 1T, that's 1,000 kilograms right there. So we can look here and say, really, 1,000 kilograms if you have 0.1T, that all that means is that you would be moving the decimal one spot right there. So it would still be 100 kilograms, which is pretty insane. If a phone weighed 100 kilograms, you would not have a phone. You would have to cart it behind you on a very large cart or truck or something like that. It would be almost too heavy to pull in a cart. That would be like 220 pounds. So this one seems to make the most sense. 150 grams. Let's change that just for the sake of comparison. Let's change that here to ounces, which we're a little more familiar with in our good old US of A. So let me go back to here. Yep, that's the one I want. 1 ounce, about 28 grams. So if we're doing this, getting rid of grams, put grams on the bottom so that it cancels. Ounces will go up here, and 28 grams, the same as about 1 ounce. We work this out. 150 divided by 28 ends up being, keep closing that, 150 divided by 28 ends up being about 5.36 ounces, somewhere in that range. So 5.36 ounces. I could make this approximately equal to, it's not exactly that, but that seems to be a reasonable answer to me. So 5.36 ounces, less than a pound, less than a half a pound. I would want my phone to weigh less than a half a pound for sure. That's a little over a quarter pound. And now let's check out number 9. So the outside temperature on a snowy day is about, if you forgot this, definitely let's go back to one of our notes here. So if you go back to 8.3 to remind yourself of some stuff. So you have a very cold day, freezing point of water. It's going to be colder than the freezing point of water if it's snowing. That would make sense. So we should have something less than 0 degrees Celsius. If we look here at our choices, 18 degrees Celsius would be much too warm. Negative 2 degrees Celsius, that seems like it would be reasonable. And I would say choice C, well, that would, to me, that would also make some sense, but that would be like just insanely cold too. So I don't really like the fact that they have 2 negative temperatures here. We could be in like Antarctica or somewhere in the Arctic, and it could be negative 40 degrees and snowing degrees Celsius, but outside temperature on a snowy day, I think what's most reasonable in most places would be choice B. So this one, I would say negative 2 degrees Celsius is most reasonable, something like that, if you had to give an explanation. And this would be choice B. Up here, this one was choice C. So that all is looking good. So we will move on to this one now. How many times greater is a square meter than a square centimeter? So square meter and a square centimeter. So remember, when we're squaring things, we basically have to take how many times bigger it is and multiply it by itself. That is what we're doing. So if this was, let's say we had 1 meter here, 1 meter here, how big would this be over here? This would be 100 centimeters, because that's equivalent to 1 meter. This would be 100 centimeters. So how many times bigger is this 1 meter squared right here compared to the units in centimeters? This would be 100 times 100, which is 10,000. So we have 5 digits or more here, leave a space after 3 digits, and so this would be 10,000 times larger. Or you could say 10,000 times greater. I said larger. Same difference. So now a cubic meter, then a cubic millimeter. Let's draw over here more of a three-dimensional shape now. Cubic meter would be something like this. We'd have 1 meter, 1 meter, 1 meter. That'd be 1 cubic meter. And then all of these now would be 1,000 millimeters. So the base, the length, the width, and the height would all be like that instead. So these are all 1,000 millimeters. So that means here we'd have 1 times 1 times 1. Here we'd have 1,000 times 1,000 times 1,000. So what's 1,000 cubed, in other words? 1,000 times itself 3 times. And so if you put that into a calculator, you'd have 1 times 1 times 1 would be 1, then you have 3 zeros, 3 more zeros, 3 more zeros. So you'd have a 1, a space, 3 zeros, space again, 3 zeros, another space. Those are kind of wide gaps. I didn't need to make them that big, but that's just the way it turned out. So 1,000 times, oh, I'll say greater this time since they used the word greater. I won't go against the grain this time, I guess. So 1 billion times greater. So I'm pausing here. I'm hesitating because your book went off kilter here and put commas in there. So I'm just trying to get in good habits for this chapter. We want to use no commas. We want to use spaces. So let's put that without the commas. Put it with the spaces instead. So that is that one. That's those two. Let's move on to number 12 now. Converting 452 inches to centimeters. We've already had a bit of practice with this as we were doing stuff like this just for comparison. And so this would be a pretty simple problem, I think. 452 inches, not 45 inches, 452 inches to centimeters. Put it over 1, make it a fraction. Makes it easier to think about, I think. And then how many centimeters was in an inch again? We look back here if you forgot. 1 inch to 2.54 centimeters. This is the table I will give you. A lot of the other tables, though, I will not be giving you. So this is a table you don't have to memorize, but most of the other ones you will have to have memorized. So 452 inches, that's going to be, I'm going to be getting rid of inches, so I'll put inches on the bottom here, centimeters on the top, and I've got 2.54 over 1 inch. This gets rid of my inches, just like I want it to happen. Now I have 452 times 2.54. On the bottom I'm just going to have 1 times 1, so no need to really think about that beyond this step. So this times 2.54 is 1148.08. And again, we're not considering significant digits here. There is some rounding error with the 2.54 thing here. A lot of these metric conversions have rounding errors here. This is not exact conversions. These decimals keep going on for most of these in most instances. But this is a pretty good estimate, at least. So we can say this. If you're concerning significant digits, there would be some of these digits we would leave off because we couldn't say that with this precision or this much accuracy. But again, we're not getting into that right now. So let's take a look at number 13 here. This is the, I'm not sure if that's a different, that must be, I was gonna say Mexican, that must be Spanish. Okay, Obra. The JW Marriott, this is 150 meters. So how far in yards is the Marriott from the sign? So there's this Marriott hotel, it looks like, here in Cancun, Mexico. So 150 meters. We just basically had to pick out that, oh, this is 150 meters, okay. And we want to change this to yards. And so we're going to say this over 1. And let's see if they got a conversion for yards. In this one, they sure do. 1 yard is 0.9 meters. So we're going to use that, even if it's not the best approximation. We're going to use what it gives us there in the table for the purposes of what we're doing here. So I want to get rid of meters. That goes on the bottom. And this was 0.9 meters to 1 yard. So that's the conversion. It's the unit fraction I'll use for this dimensional analysis. The meters go away. And then I have 150 times 1 and I have 1 times 0.9. So all I really have to do is 150 divided by 0.9. And what does that give me? That gives me about 166.67 if I go to 2 decimal places, which I'll do here. So about that many yards, and I would want to round this off too. So I'll put my as one of my students in their class so eloquently put it, my 2 strips of bacon. I've got the approximately equals to sign. I have this many yards, so about that many yards, which is a reasonable answer too, because a yard is slightly shorter than a meter, and so this should be slightly bigger when we convert the units that way. All right, let's check out number 14 now. 14, changing -10 degrees Fahrenheit to degrees Celsius. So this was coming from 8.3. We had those formulas. Here we are. So we're going to use these formulas right here. So from Celsius to Fahrenheit, we plug it into this one. And so let's use the 9/5 C plus 32, converting Fahrenheit to Celsius. So F is 9/5 C plus 32. Plug in the number. I think, yep, there's a mistake. What did I do wrong there? Whoops, wrong one there. So this is converting from Celsius to Fahrenheit, but I'm changing this from Fahrenheit to Celsius. So I actually want to move this. Let's see if I can pick all that up. Sure, that's fine. I'll move this over here and just change that to a 13. Right there. That. Or 15. That's what I meant to say. And then 14 over here. What are we going to use for changing Fahrenheit to degrees Celsius instead? From Fahrenheit to Celsius, we want to use this equation. If you don't remember this one, you can always, if you at least remember this one, you can always derive the formula by solving for C here, subtract 32, multiply by 5/9, and you get this formula instead. So hopefully you're going to remember both of these though. So let's take this one. I hope you do get those memorized, but at the very least, you need to have that one memorized. So 5/9 times the quantity F minus 32. So C equals 5/9 times the quantity F minus 32. And so I plug in my -10 right here, and I simplify this. So this becomes 5/9 times, this will be -42. I could make that a fraction if I want. I put it over 1, and then this I'm going to multiply through. So this is 5 times 40 is 200, and then 5 times 2 is 10, so that's going to be -210 over 9. And that's about, if you plug this into a calculator, that's going to be pretty cold there. 210 divided by 9 is about negative, that'll be 23.33, but we have a negative out in front of there, so 23.33 degrees Fahrenheit. Kind of depends what they asked for. They didn't really say how to round it here, so I went with 2 digits. You could have gone with 1 or maybe in the nearest digit. Just make sure you do what it asks you to do. And so 20 degrees Celsius now. 0 is freezing, and 20, if I remember right, that should have been kind of a comfortable temperature. We go back to, nope, we go back to this here. So 20, a temperate day. I'll pretend you didn't see that right there, and let's plug it in and see what we got. So this is 20 right there. Now we're not adding 20 and 32 first. We don't have parentheses here, so we're going to multiply this through first. So that, I can make a fraction like that. I can make this easier by cross canceling if I wanted to. So that would become a 4 and a 1. They both can be divided by 5 in that way. And this becomes 9 times 4 is 36. It's 36 over 1, which is just 36. And so we add 36 and 32. And like I expected, I looked at the other table before, and it was 68, and we got the same thing. So 68 degrees Celsius. Alright, now moving on to 16. A giraffe may be 12 feet tall. How many centimeters is this? And so I don't have a conversion here that goes directly from feet I lied. I do. I have one that goes right from feet to centimeters, so I can use that one. If I didn't know, I could do two conversions. I could do one after the other. Kind of disappointed in the book that they didn't give us one where you had to do multiple conversions, but you can go back to the lesson on 8.4. Plenty of examples that I did in that lecture that would help remind you of how to do ones with multiple conversions that had to be made. So a draft maybe 12 feet tall. So we're going to say 12 feet. That's what we're starting with. We want to change it to centimeters. I'll put that over 1. I'll put feet on the bottom. And the conversion was 1 foot to 30 centimeters. If you ever look at a foot stick, I guess for lack of a better term, or like just a regular ruler that's usually a foot long, 30 centimeters matches up quite well with that actually. So this is a good approximation here. So this is 30 centimeters right here. By putting feet on the bottom here, I get rid of feet on the top here, and I multiply this through. 12 times 30, well 10 times 30 is 300, 2 times 30 is 60, so that's going to be 360 centimeters approximately for that draft. In other words, that would be about 3.6 meters if you change it to meters. And then if you, I think just to make a point here to remind you of something, let's do this. Let's pretend that you wanted to change feet to inches first, and then you wanted to change inches to centimeters next. So let's see what that would give us instead. So if I did that, just to show you that multiple conversion step way, in case that shows up, it probably will show up on the test, so I want to show you one like that here. Let's say 1 foot is 12 inches. That's something we just need to know. If we go back to this lesson here and go back a bit, these ones you just have to know. You need to know these. These should be things, for the most part, that you've known all your life and have used all your life, but there might be a couple of extra ones here that you're going to have to memorize. So anything I've handwritten, definitely stuff you need to have memorized. But here I'm going to change this to inches now first, and then I'm going to change inches, convert inches into centimeters by doing this. I already used the fact that 1 inch was 2.54 centimeters before approximately, so I'm going to use that. That will get rid of inches. Now it's a matter of multiplying 12 times 12 times 2.54. So 12 times 12, that's 144. And I multiply that by 2.54, and these should jive together pretty well. So 365.76. You'll notice that's a little different, but that's because one of these was a better approximation than the other. My instinct says it was this one because 30 centimeters on a ruler was so much closer, but I think it might actually be this one the more I think about it now. Not exactly sure what would be best. I would have to go to internet and check that out and see what I would get. And I was too curious not to check. So 12 feet, 365.76 is the better answer there. So this idea that, oh, yes, going back, there we go. This idea that 2.54 centimeters was 1 inch. 1 inch was a better approximation than 30 centimeters to 1 foot. So this is the better answer, but this is pretty good too. It just depends on which conversion you're using. But the better answer again was this one. And then the final one, I believe, there's two more actually. Yeah, there's two more. So second to last one. This one we got a fish tank in an aquarium is 20 meters long by 20 meters wide by 8 meters deep. So let's draw a picture of something like that. So I would say this is going to be 20 meters long, this will be 20 meters wide, and then 8 meters deep. Maybe something like that. So I'm just drawing kind of this box type shape. And I'll give it some labels here. Definitely not my most artistic work right there, but I think we get the point. This is 20 meters, this is 20 meters this way, this is 8 meters deep. So I'm saying there's water in here, and so there's some fish in here maybe. Let's see how ugly I can make my fish. Someone's got a snaggled tooth right there. So there's some fish in here. And determine the volume of the tank in cubic meters. So in cubic meters, that should be pretty easy. I know that the volume of any box is just length times width times height. So this is just going to be 20 times 20 times 8. I know 2 times 2 is 4. 4 times 8 is 32. And then I have 2 more zeros to add to that. So this would be 3,200 meters cubed. Now we're doing a volume. Volume, we're multiplying 3 dimensions times each other, so that's meters cubed. Now we're changing this to determine the number of liters the tank can hold. So if we go back to one of our notes from before, we would recall that 1 cubic meter is 1 kiloliter. So 1 cubic meter is 1 kiloliter. 1 decimeter cubed is 1 liter. 1 centimeter cubed is 1 milliliter. So we're going to use this right now and say 1 meter cubed, that's 1 kiloliter. So if that's true, if 1 equals 1, then 3,200 would equal 3,200. But that's in kiloliters. This asks for the number of liters. So to change kiloliters to liters, again, think about this. Kangaroos hop ditches but don't catch mice. How many spots are you going to be moving that from kiloliters to liters? That's 1, 2, 3 spots to the right. Liters is your base unit here, and so this becomes a 3 and then a 2, 0, 0 and 0, 0, 0 after that. So we're going to change that. That would be 3,200,000 liters. And then finally from there, part C. Now the back of the book says how many, the question asks how many liters, but then it has the answer in kiloliters with in parentheses. I don't know why they did that. They asked for liters, so why would you put that there like that? I don't know. But determine the weight of the water in kilograms now. And so we hopefully remember from a previous lesson, from one of the lessons we learned, that each liter, 1 liter, is the same as 1 kilogram of weight. So 3, 2, 2, 0, 0, 0, 0. 1 liter is 1 kilogram, so this is the same as that many kilograms. And if you forgot where that idea came from, that was in lesson 8.3. So this was talking about mass and temperature, this lesson. On this, just verify that, yeah, that was mass and temperature. And so the mass of 1 meter cubed is a kiloliter, that's a metric ton. The 1 liter here matched up with 1 kilogram. If you pick up a liter bottle of water, that weighs 1 kilogram. So that weighs about 2.2 pounds, in other words. So this looks all good to me now. Let's do what is now our last one. So number 18 looks like a pretty involved question here though, so let's buckle down and see what we got. The cost of paint. The first coat of paint for the outside walls of a building requires 1 liter for each 10 square meters of wall surface. The second coat requires 1 liter for every 15 square meters. And so that makes sense to me. You'd have to use a little less paint. You've already got 1 coat on there. The second coat should go on a little easier, not quite as thick. If the paint costs $3.50 per liter, what will be the cost of 2 coats of paint for the 4 outside walls of a building 20 meters long, 15 meters wide, and 6 meters high? So lots going on here, but first of all, let's draw a picture. That's going to be extremely helpful. So let's draw a picture of my building. I'm just going to draw the outside part of the building, the 4 walls basically. So I've got, let's say this is almost there, almost there. This is 20 meters long this way. This is 15 meters wide this way and 6 meters high. So how many 4 walls? How many walls do we have? We have 4 walls. Just said that in the question. And so think of this kind of being back there too. So we're going to paint this front wall, this side wall, the back wall back here, and then this left wall as well. We've got those 4 walls to paint. And so let's figure out first what's the area of the 4 walls together. So area of the 4 walls. That's what we need to calculate first. So wouldn't this one be 20 by 6? I hope you would say yes to that. 20 feet long, 6 feet high. So we have one that's 20 by 6. We've got a second one that's 15 by 6 right there. And then that repeats. So we have another one back here that's 20 by 6, and this one is 15 by 6. So we're going to add all this together. Could you say you have 20 times 6 times 2 because there's 2 of them? Yeah. Could you say it's 15 times 6 times 2 and just add 2 times this and 2 times that? Just add that together? Yeah, it gets you the same thing. So that's fine. If you do it that way too, this will be 90 and 120. You got those things twice. Add all that together. You got 210 plus 210 is 420 meters squared. So this is how much area you have to paint. So this is the area to paint. Let's make a little note of that. This is the area to paint. So we're trying to figure out paint cost will be the cost of 2 coats of paint. So our first coat is going to be 1 liter of paint for each 10 square meters of surface. So let's make a little delineation of the data here. The first coat is going to be 420, and I'm going to divide that by 10 because it's every 10 square meters of surface we're going to need a liter. So this, cross out a single 0 if they both have the same number of zeros. We can just cross that out. And then this would be 42 left over divided by 1 is just 42. So for the first coat I'm going to need 42 liters for the first coat. For the second coat, it's still covering that same area. It's still covering 420 meters squared, but I'd be dividing that by 15 now. This one I can put on a little thinner, so I already got that first coat established. Then 420 divided by 15, that one I'm not so sure off the top of my head, so I will use a calculator, and that gives me 28. Okay, so 28 liters for the second coat. Now if we put that together, this is going to be 70 liters total that we have to buy of paint. It's 42 plus 28, and so now we take our total cost is going to be, since each liter costs $3.50. Whew. Talk about some steep inflation. So this would be 70 times 350. So it's times $3.50. This would be, I think I've got that in my head. I just want to double check it. Yeah, $245 now dollars. So $245 for the whole project to buy all the paint you need to do the 2 coats like that. So hey, let me know if you had any questions. You can come in here in my class before or after school to ask me questions. Hopefully you found this extremely helpful in preparation for your test. I'm hoping that you're utilizing these well and that you kind of skipped around if you didn't need help with all the problems, that you just watched what you needed. But as before, make sure for extra practice, if you're still like, I'm still kind of weak on a certain subject or a certain topic within the chapter, go to the Chapter 8 review on these pages in your textbooks. All of the answers are in the back for those. So check your work as you go and make sure you're ready for that Chapter 8 test coming up soon. Alright. Hope you guys have a great day.